Assalamu alaikum dear students, and welcome back to engineering geology and seismology course. As you all know that we have talked about and discussed the engineering geology part of this course in our midterm. So in final term we will talk about and discuss the seismology part. So today we are going to jump in and introduce you to some basic topics and subjects related to the seismology. So let's start. Seismology is the scientific study of earthquakes and how waves propagate and move themselves through the earth. So seismologists are kind of like people who interested in acoustics. It's how waves and energy are moving through a medium size. Most is Greek for the word earthquake or earth, and logos or logi is associated with the word they don't study or science. So it's the science of earthquakes or the science of the earth or the mechanics of the earth. The seismologists are unique people because they have the ability in essence to look, and I have this in quotation marks, right, look into the earth by interpreting seismic waves and how they travel through the earth's center. Because of the seismology we have learned how our earth is constructed, and we have learned that it used to be people thought that the earth was like an egg where we live on a shell, and then there was the yolk of the middle, but it's shown to be a part of a lot more complex than that. There are really multiple layers associated with the earth, and those layers are shown in this cross section shown here. That looks kind of like a piece of pie. Turn it upside down depending on where you are. The thickness of what we are talking about or the particular component of the earth can vary. So for instance, for oceanic crust, we generally say that the oceanic crust is around 5 kilometers thick, and while it may sound like a lot, it's really not 5 kilometers, it's extraordinarily thin. So oceanic crust is very thin, very brittle material, contrast that with the continental crust. So the continental crust is like this stuff shown here where the mountain ranges are, and you can see that it's a lot thicker than the oceanic crust over here beneath the ocean. So the continental crust varies in thickness between 25 to 75 kilometers, just depending on where you are located. Then if we move below the crust, we get into what's called the lower lithosphere. So the lower lithosphere is this stuff that I am highlighting, that I have highlighted it right here, and a lower lithosphere ranges in thickness between 5 or 50 or to 120 kilometers thick. Below the lithosphere is the asthenosphere, which is around 200 kilometers thick, and then below that the lower mantle is 2500 kilometers thick. The outer core is 2200 kilometers thick, and the inner core, we know this very precisely, is 1278 kilometers in radius is the inner core. And we know all this stuff because of the way that seismic waves that have traveled through the earth and the way they reflect off different boundaries. Now, since we have able to record earthquakes, seismologists have shown that most earthquakes occur in the lithosphere. In the other words, they occur in the upper 200 kilometers of the earth. Basically, in the ground surface, if you go down beneath the ground, generally in those upper 200 kilometers, you are gonna have almost all of the earthquakes occurring. But some earthquakes can occur in the asthenosphere and in the upper portion of the mantle. However, no earthquakes have ever been recorded below the depth of about 1700 kilometers. So the driving theory behind why the earthquakes happen is what's called the theory of plate tectonics. This is something now we teach taught in universities, and it's a very good theory, and there's a lot of evidence to support it. And the idea of plate tectonics is that the lithosphere, or the crust of the earth, is divided into different portions that we call plates. And the plates are constantly interacting, bumping, grinding against one another because of the movements and the convection and the things that are happening beneath the lithosphere down in the mantle. So the theory of plate tectonics is credited originally to a geologist by the name of Wagner, and he published the paper in 1915, and it really is a tragedy because Wagner published this paper and he was mocked by the scientific community. Not just mocked, he was shunned. Everyone thought it was crazy because everyone knew that if plate tectonics were real, that implied that there are all the earth was created known in one location, and that's the stuff that have been moving for a long time, and that can't possibly be true. So basically the scientific community call him a fraud or a freak, and it ruined his career, and he died not too many years later as a discredited and a poor of scientists that nobody believed. But later on, the evidence started to pile up, and people realized, like, wow, this guy was actually right, and that the thing that he was indicating sound reasonable and seem to explain different evidences that they are seen. So based now on modern theory of plate tectonics, we know that we have 7 we call major plates. These are very large tectonic plates, and the 7 plates are the Pacific plate, the North American plate, the Eurasian plate, the South American plate, the Indian plate, the Antarctic plate, and the African plate. So let's just take a pause and the lecture and go ahead and write down these in your notes, okay? I think you should be back now. So after you wrote those down in your notes, in addition the seven major plates, we also know that there are seven minor plates. So these are smaller plates. They are still kind of under debate. People don't aren't really sure where the boundaries are, so they have kind of created their own category for these type of plates, and we call these plates the Juan de Fuca plate, the Caribbean plate, the Nazca plate, the Cocos plate, the Philippine plate, the Arabian plate, and the Scotia plate. So, as I have mentioned before, I'll go ahead and pause and write those down, and you can unpause when you get your video notes or lecture finished. So, like I said before, the theory of Wagner was mocked until all the way until the 1960s, and then the evidence has really started to pile up. And these evidences include the recorded location of earthquakes fossils, recorded magnetic seafloor mapping, hotspots, and geodetic mapping. So these are the evidences that began to rear themselves in the 1960s. So in the 1960s, the 1960s is not that long ago, and I want you all to appreciate and understand that when we are talking about our modern understanding of earthquakes and how the earth works, these are all new theories, and we are still proving them or still testing them. So it's kind of exciting when you think how new this field of science is. So let's talk about each of these different evidences. This evidence of map earthquake location is pretty overwhelming, and it shows that where there's got to be something going on. So this is a map of all of the known earthquakes to have occurred between 1977 and 1992. And what do you see? You should be seeing patterns, or that the earthquakes tend to follow boundary lines. So these boundary lines, scientists begin to say, like, wow, those maybe, this plate tectonic theory isn't that bad, and those locations where the earthquakes are occurring, maybe those are the plate boundaries. So this was the first evidence that we started to see. Another evidence that indicated that the continents were together at one point and weren't always separated was the evidence of fossils records. So you can kind of see the different shapes. We have South America here, we have Africa here. So let's see, this look like Australia, and this is Antarctica, and this is Indian or Asia. Okay, so we have all of these different continents here, and what we see is, or what the paleontologists or paleobotanists have seen, is that, for instance, a very rare and certain type of lizard fossils was observed in this general region. but it was serving both continents, South America and Africa, same with this kind of crocodilian looking fossils. As they started to line up where these fossils were found and identified, they started noticing, hey, if we piece these continents together, the location of these fossils kind of match up. So that began to be kind of interesting evidence. One thing I find really interesting that even in 1915, when the scientific community mocked Barguiner for saying that the continent at one point had been together and that the continental drift had occurred, isn't it neat to know that we have enlightened knowledge and that tell us for a long time that all of the earth used to be together and that we had one mass of earth, and now we have the different continents. But it's kind of neat that we have that enlightened knowledge evidence. Number 3 is that we have magnetic sea flooring mapping. So this really stemmed from World War II, and what happened is that the different militaries, we wanted to map very accurately the sea floor cannon, so their submarines could sneak around and lurk and strike if they needed to. This was more so a Cold War kind of thing, and so they started mapping the seafloor with all different types of instruments, including a magnetometer. And when they started looking at the magnetometer records from the military, they started seeing some very freaky patterns. So every ocean has what we call a mid-oceanic ridge or a spreading ridge. This is like a mountain range that runs right down the middle of the oceans, and when they started mapping the sea floor, they started noticing pattern of polarity. Now you may or may not be aware of this, but the polarity of the earth, if I draw the earth up in the top of the world we have north, and down on the bottom we have south, and compasses point north. There have been periods, many periods in the earth where these poles switch and north is actually in south and the south is in the north, and then the poles switch back again. And what we have seen are over hundred and thousand of these polarity switches in the history of the earth, is that when new magma comes out of the spreading sea floor ridges, the new magma is rich with iron. And if you have played with magnets as kid, and that iron is very magnetic. So guess what happens in the magma when it comes out of these spreading ridges? That's right, the iron lines up according to the magnetic north. So when they would run these magnetometers across the seafloor, they would see patterns where all of the iron was aligned in a certain way, but it was similar on both sides of mid-oceanic ridge. And what that implies is that over time, as magma is coming out, it's pushing the oceanic ridge in both directions equally, and so based on whatever the pole is of the earth at the time. The iron lines up according to that, and then it's like a conveyor belt. The oceanic crust just gets pushed out and gets sliding away from the spreading ridge, but the magnetic record is locked in the oceanic crust. So again, another evidence of seafloor spreading or continental drift that's going on, evidence number 4, is what we call hotspots. Now there is certain location in the earth that we know, for whatever the reasons, the mantle is very close to the crust of the earth, and in these locations they tend to produce lots of volcanic activity. One of these hotspots, for instance, is the island of all of Hawaii. So if we look at the map of Hawaii, and not just of Hawaii but just a map of seafloor chain around Hawaii, we tend to see, there's the big island right there that I have circled it with the red circle, but you have the Hawaiian chain, and it's spread for hundreds if not thousands of miles out, but chain turns and we have underwater mountains. If you follow this, it doesn't take a scientist to see that this chain of mountain kind of makes a line and that stop at Hawaii. So why do they stop at Hawaii? Well, cause guess that what's below Hawaii is the most volcanically active. So as you move away from the big island, the volcanism gets less and less, and also the islands get smaller and smaller because they are eroding. They were formed longer ago, when they were formed when that portion of Hawaii or the chain was located over the hotspot. So what is now the big island, someday in the future, may 3 or 4 or 5 million years in the future, it's gonna look like that, and there's gonna be new islands being formed. So that's kind of a need. And the one interesting thing is the Yellowstone happens to be the hotspot that's closest to you right now. The Yellowstone is the super volcano, and we know that it happens to be a hotspot. So all of those evidence that we just talked about, the last 4 are pretty convincing, but nail in the coffin is what we call geodetic survey. So this is where now we use technology to get an independent frame of reference that's above the earth, and that we can measure within centimeter or millimeter accuracy movement of itself. So we set up these very high precision GPS trackers, and we just watch them. And as we have done this and we have monitored the movement of these trackers, these arrows on this figure shows that we have observed, and this is really indisputable evidence that things are moving, the continents are moving, they are being pushed around. And so we don't really dispute the theory of plate tectonics anymore. In fact, a lot of people are pushing to say it's not a theory anymore, but it's a law or it's a fact, and that's really hard to do in scientific community, and we still call it a theory, but the evidence are really overwhelming, and that it is indeed a real thing. So that would be all for today's lecture. If you guys have any questions or any difficulties in understanding this, you guys can ask. You guys can find me through this email. So take care of yourself. Thank you so much.